Distributorless Ignition. Part 2, Electronic Ignition Systems and EST. In the last program, you were introduced to the breaker point ignition system. You saw how this system transformed low battery voltage to high spark voltage by using the principle of induction in the ignition coil. In this program, you'll examine the next major innovation in ignition systems, the electronic ignition system.
The breaker point system provided ignition in all types of automobiles for several decades. However, as fuel prices rose and the federal government mandated exhaust emission controls, engineers were required to design a more fuel-efficient engine that produced less harmful exhaust emissions. The simplest way to improve fuel economy and reduce harmful emissions was to design an engine that uses less fuel. But this obvious solution had one drawback.
A lean air-fuel mixture requires higher voltage to jump the spark plug gap and initiate combustion. In order to build an engine that could burn a leaner mixture, automotive engineers needed to design an ignition system that could supply higher voltage to the spark plug. This requirement doomed the breaker point ignition system. Here's why.
Remember, in a breaker point system, the high voltage needed for combustion is transformed from low voltage by using the principle of induction. This is achieved by breaking the primary circuit and collapsing the magnetic field in the ignition coil's primary windings. To increase the system's overall voltage output, it was necessary to increase current input into the primary windings, because greater current creates a stronger magnetic field. Collapsing this stronger magnetic field induces higher voltage in the secondary windings.
Simply increasing current flow wasn't possible with the breaker point system because the metallic points have a limited current capacity. With increased current, the current would overheat the points and burn the metal contacts. Since current into the primary windings first flowed through the points, it was impossible to allow more current into the primary windings without quickly melting and destroying the points. A new means of controlling the primary circuit's higher current was needed.
In the mid-1970s, automotive engineers turned to the transistor, and electronic ignition was born. The transistor can serve as an electronic switch. It's commonly used on many electronic components. You've probably heard of transistors being used in radios, televisions, and other electronic devices. Transistors are an ideal substitute for breaker points because they allow the system to send higher current into the primary windings and to cut off current flow quickly and efficiently. Let's take a closer look at how a transistor works.
This is a schematic representation of a transistor. A transistor is made up of three parts: a base, an emitter, and a collector. In a transistor, a low current at the base will allow a higher current to pass through the emitter and out the collector. By cutting current flow to the base, current is also stopped at the collector. Automotive engineers realized that this transistor could be used to control primary current and collapse the magnetic field in the primary windings. Now let's look at how engineers incorporated the transistor into an electronic ignition system by looking at the system's components. Most of the components will be familiar, since they were also present in the breaker point system. For example, electronic ignition still uses an ignition coil, a distributor, and spark plugs. However, inside the distributor, there are no breaker points. Instead, the system uses a transistorized ignition module with a reluctor and pickup coil. Here's how these components work together to generate an ignition spark.
Remember, the principle of induction states that a wire moving through a magnetic field will create or induce current flow. Automotive engineers also use induction to send timing or triggering pulses to the transistorized ignition module. As the distributor shaft rotates, the reluctor turns inside the magnetic pickup coil. The reluctor is made of an iron compound that is strongly attracted to magnetic fields. As it passes across the pickup coil, a low-voltage pulse is induced by the moving magnetic field.
Here you can see induced voltages on the multimeter as this reluctor spins past the pickup coil. The pulses from the pickup coil are synchronized with the timing needs of the engine. Here's where the transistor does the job of the breaker points. The voltage generated in the pickup coil is sent to the base of the transistor. When the pulse enters the base, it closes a circuit and allows a stronger current to pass through the emitter and collector and then to the primary circuit. The low voltage received at the base of the transistor acts as a switch to complete the circuit and allow current into the primary circuit. Current into the primary circuit of the coil creates a magnetic field around the primary windings. In order to induce high voltage, the transistor breaks primary circuit flow, as the points did in the breaker point system. This collapses the magnetic field and produces a high voltage in the secondary windings.
An electronic ignition system produces a higher voltage spark because it allows a higher current into the primary windings. The higher current, in turn, produces a stronger magnetic field, which, upon collapsing, generates higher voltage in the secondary windings. All of this is possible because transistors are able to handle higher primary current than breaker points. Now that you have seen how an electronic ignition system is able to provide a more powerful spark, let's take a look at how electronics are used to control ignition timing.
Most modern automobiles are equipped with an onboard computer that controls many engine functions. Once a car is running, this computer allows another significant improvement over the mechanical breaker point system: electronic spark timing. The General Motors Electronic Control Module, or ECM, monitors timing in an electronic ignition system. The ECM is linked to the distributor's ignition module by a 4-wire connector. These 4 wires represent circuits called high energy ignition, or HEI reference, electronic spark timing, or EST, bypass, and ground. The 4-wire connector acts as a feedback loop that controls information between the ignition system and the ECM.
The ECM uses information about changing engine conditions to decide when to signal the ignition module to deliver current to the coil. The system allows continuous timing control by the car's computer. Here's how it works. As the engine is cranking, the pulses generated by the pickup coil signal the ignition module to switch current into the primary circuit. However, these triggering pulses are also sent from the ignition module to the ECM. When the ECM senses the engine is running, it begins to control engine timing by sending its output back to the ignition module through the 4-wire connector. In a running engine, the ignition module doesn't send primary current into the ignition coil until it receives triggering pulses from the ECM.
How does this improve ignition? The system works better because the ECM can control when triggering pulses are sent to the ignition module. The ECM is programmed to vary the triggering pulses according to engine conditions. The ECM receives information from sensors located throughout the engine. These inputs are processed by the computer, which then decides the proper time to send its triggering pulses to the ignition module. In a running engine, the controlled release of the ECM's triggering pulses ensures that spark is delivered in the combustion chamber at just the right moment. In this way, the computer controls ignition timing electronically and responds more quickly and accurately to changing driving conditions. The ECM is able to regulate spark timing much more efficiently than was possible in the breaker point system.
Electronic ignition systems were a major advance in automotive technology because not only was the system capable of supplying higher voltage to the spark plugs, but also, with the use of a computer, it could precisely control when spark was delivered based on input from throughout the automobile. Now let's review the key segments of this program. 1. Electronic ignition was developed to generate the more powerful spark needed to ignite leaner air-fuel mixtures.
2. A transistorized ignition module can handle higher primary current than breaker points.
3. On a running engine, the ECM controls timing based on input from sensors located throughout the car. In the next program, you'll see how breaker point and electronic ignition systems have evolved into today's distributorless ignition, which uses the waste spark concept.